Hello and welcome to Doc Clay's Chemistry Lessons. Today we're going to be looking at AQA A-level chemistry and entropy and free energy. So by the end of this lesson then we should be able to explain, describe and calculate changes in entropy and explain and describe Gibbs free energy and how it relates enthalpy and entropy changes to the feasibility of a reaction. Also, if you're looking for any of our other lessons, please remember to check out the YouTube cards by clicking the I at the top right hand corner of this screen and throughout the rest of the video. So first of all, let's go and have a look at entropy. Entropy then is simply a measure of disorder, and we often measure entropy changes, and we would say that something which is more disordered will have a more positive entropy. The other thing that we state about entropy here is we give it a descriptive letter of S if we're talking about absolute entropy, or delta S if we're talking about the change in entropy, and it also has units here where we're looking at joules per Kelvin, so it's now got a temperature reference per mole. And notice how this is different here to enthalpy changes, where enthalpy changes are in kilojoules per mole. So our entropy value now has a temperature reference in Kelvin. That should be Kelvin -1, sorry. And should also be, and the entropy is in joules, whereas our enthalpy is in kilojoules. So there's a factor of 1,000 difference. So when we're doing our calculations later on, we'll make sure we have to include that factor of 1,000 difference in any calculations. We can describe entropy then and its effects and changes by looking at 3 individual cases. So our first example here then is by looking at the physical state. And if we're looking at this physical state, we have solid, which is then heated to make a liquid, which is in turn heated to make a gas. As we move between the solid to the liquid to the gas, we observe an increase in entropy, and therefore the entropy value is becoming more positive as we go between the states. The second example then is dissolution, or dissolving as we normally call it, where we observe the solid being dissolved into a liquid and becoming an aqueous substance. So we've got solid on the left going to aqueous here on the right. And again, as we move from the solid to the aqueous solution, there is an increase in entropy, and that's because there is more disorder. There's a greater possible number of arrangements of particles in the aqueous than there is in the solid. Because the solid state, they're all in one fixed position. So once again, we've a more positive entropy value. Just going to complete here the solid, the liquid state and the gas on my drawing. The final example then is looking at the number of particles. Here we've got fewer molecules on the left and we've got more molecules on the right. And because we've got more number of molecules, we got more possible ways of arranging those particles, and again, therefore, we're observing an increasing value in the entropy. And therefore, we've got a more positive value as we move from left to right. So these are 3 examples, and what we're going to do now is we're going to see how these we can predict what the entropy change would be, and also how we can actually do the calculation of entropy change for particular reactions. In this slide then, we're going to look at predicting and calculating changes in entropy. We're going to look at predicting the changes to start off with, and then we'll go and have a look at actually how we do some fairly simple changes in entropy calculations. The entropy change we define as the entropy of the products take away the entropy of the reactants. So we can have a look then here at some examples of entropy changes and see if we can predict what the entropy change would be. So this first one then, we've got sodium chloride solid and sodium chloride aqueous. Because we've got an aqueous solution from a solid sodium chloride, we expect the sodium chloride aqueous to be a greater entropy value, and therefore the difference between these two means that the products would be greater than the reactants, and so this would be a positive entropy value. As we look at the second example, we're going from a sodium chloride liquid, which is a more positive entropy value than the sodium chloride solid, and therefore the change in entropy here we would expect to be negative. Number 3 here, where we got ozone gas going to 3 oxygen gas. Well, here we're going same state, but we're increasing the number of molecules, and therefore the products would have a higher entropy value than the reactants, and this would therefore be positive. In this next one, where we're actually looking at the Bourne Haber cycle, where we got N2 nitrogen gas plus 3 hydrogen gas going to 2 NH3 gas. Well, here we're all in the gaseous state, but we're going from a total number of 4 molecules down to a total number of 2 molecules. Therefore, our products have got a lower entropy than the reactants, and therefore we'd expect this entropy change to be negative. In the hydrogen plus iodine going to 2 hydrogen iodides, well, we've got 2 gaseous states in the reactants and the products. We've got 2 moles of gas on the left, and we've got 2 moles of gas on the right. So this example, we would actually have to do some values, but we wouldn't be able to identify or predict what the value would be here, and it would probably be fairly close to 0, but we'd have to do the calculations to check. In our final example here then, we've got copper carbonate going to make copper oxide and carbon dioxide, which is a thermal decomposition. We're going from 1 solid molecule to 2 particles, where one's a solid and one's a gas. So we'd expect in both counts the products to have a greater entropy than the reactants, and therefore this would be positive. In this final example then, we're actually going to look at some calculation, but before we do so, we can look at our actual reaction and see if we can determine whether we expect it to be positive or negative. Here on the left hand side, we've got ammonium hydrochloric acid, or hydrogen chloride actually, because it's in the gaseous state, and we've got 2 molecules, both in the gaseous state, going to form 1 molecule which is solid. So in both of these instances, we'd expect a more positive reactant value than the products, and so we'd expect this overall entropy to be negative. But just to check, we're going to see if we can calculate here the entropy change, where we calculate the total entropy of the products here, where we've got ammonium chloride, which we see here is 94.6 joules per Kelvin per mole, and we're going to take away from that the total reactant, the total entropy of the reactants here, where we got 192.3, which is greater because it's in the gaseous state, and we got 186.8 again, which is in the gaseous state, so greater than our solid, and we end up with an entropy change here of 284.5, and this is a negative value, joules per Kelvin per mole. So the calculations here for our entropy change are quite simple. We just got to remember that it's products, take away the reactants, and we summate all of our products. And again, if there's any stoichiometric numbers in front, we need to multiply those to add to the values. We're now going to go and see how entropy can have an effect on whether or not a reaction is feasible and whether it will go. So we're now going to look at this thing, free energy change, what it means, how we can calculate it, and what it means in terms of feasibility of reactions. So the free energy change is given the symbol delta G, and it describes a measure of whether or not a reaction is feasible. And by feasible, what we mean is one that once started will carry on to completion without any further energy being supplied to it. And our key point for all of this and for all of our calculations is that when delta G, the Gibbs free energy, is less than or equal to 0, then we describe the reaction as being feasible. Now, importantly, as we look at our equation over on the right here for Gibbs free energy, delta G, it's composed of two terms. That is the enthalpy change, delta H, and the entropy change, delta S, with the delta S having a temperature component associated with it. A couple of key things when we look at our equations later on is often enthalpy changes are given to us in kilojoules per mole. Therefore, when we're doing these calculations, we need to convert them to joules per mole by multiplying by a factor of 1000. And also our temperature here is in Kelvin. Often we're given temperatures in degrees Celsius, and therefore if we ever have to do any conversions here, we have to add 273 to our degrees Celsius value in order to get it into Kelvin. So now let's go ahead and have a look at some examples. Our first example here is one of the thermal decomposition of magnesium carbonate to magnesium oxide and carbon dioxide. And what we want to know is this reaction feasible at the temperature of 298 Kelvin, in other words, at room temperature. So in order to do that, we've got some enthalpy data, plus 117 kilojoules per mole, and some entropy data of plus 175 joules per Kelvin per mole. What we need to know is, or the question really is delta G less than or equal to 0? So in order to do that, we need to do some calculations, and we need to calculate delta G at this given temperature. And we've got a value, or an equation at the top here. We've got the Gibbs free energy is the enthalpy change. So we've got here a value of plus 117. Notice we're in kilojoules, so we're going to multiply that by 1000 in order to get to 117,000 joules per mole. And we're going to take away from this value the temperature, 298, multiplied by the entropy change here, which is in joules per Kelvin per mole, which is plus 175. So if we put these into our calculator and we do the sums, we end up with 64,900 joules per mole. And importantly, this is a positive value, and therefore at 298 Kelvin we can say that this reaction is not feasible. Now, obviously what it does mean is that at room temperature this reaction isn't feasible, but if we were to increase the temperature significantly, then we may be able to get this reaction to occur. Now then, we may be interested to know about at what temperature is the reaction feasible. Now, this is quite a useful industrial thing to know, because we may want to know whether this reaction is actually possible or not. And we can do this by simply rearranging our equation. What we know is that delta G, the reaction becomes feasible when this is less than or equal to 0, or importantly, the tipping point is when delta G is equal to 0. So at this point, we know there'll be a change in temperature, the reaction will become feasible. So we can rearrange our equation, therefore, to say at 0 is equal to delta H minus T delta S for our entropy change. And if we follow this through, then we can have T delta S is equal to delta H. And if we then just simply bring the entropy change onto the side on its own, the temperature is equal to delta H divided by delta S. And what this will give us is the temperature at which the reaction becomes feasible. Now what we can do is use our data that we've got from our question here to calculate the temperature here. And so we have the temperature is equal to the enthalpy change, which is 117. Remember here that we have to convert this, in this case, to joules per mole. So it's 117,000 over the entropy value, which is 175 joules per mole. And what we end up with, if we just round this up to 3 significant figures, is we end up with a value of 669 Kelvin. And for this particular example, because if we go above this value, then our entropy T delta S value will become greater than our enthalpy value, and therefore above this temperature delta G will be less than 0. We can actually end up with a temperature greater than or equal to 669 Kelvin. The reaction becomes feasible. So the free energy change there we can see varies with temperature, and there's a few things to be aware of here when we look at the enthalpy and entropy values. We can observe there, since we've got enthalpy and entropy values, that we can have 4 possible different states for the Gibbs free energy. We could have a system where we got enthalpy is negative and the entropy is positive. If we have that situation, then since the enthalpy is negative and T delta S is always going to be positive, and we're subtracting T delta S from delta H, then delta G will always be negative for that scenario of reactions, and therefore all experiments and all reactions will be feasible across all temperatures. Now, if we got an example of a reaction which is exothermic, or energy is released, and we end up with a negative entropy, in other words, we're getting fewer number of molecules, or perhaps we're making a solid from gases, then we can see that the delta G will be negative at lower temperatures, and that's because as we increase the temperature, our T delta S will become a more negative value, and at some point will become more negative than the delta H value, and therefore will tip, and delta G will become positive at higher temperatures. As a result, the reactions will be feasible at lower temperatures and not feasible at higher temperatures. Now, if we've got an endothermic reaction taking energy in, and we've got a positive delta S, well, this might be an example here if we were looking at a thermal decomposition. That's an endothermic reaction, and we're going to be producing gas. Well, at lower temperature, the delta G is going to be positive because enthalpy will be greater and will be positive, whereas the entropy change will be not as big as the enthalpy change, and therefore at lower T we'll have a positive delta G, while at higher temperatures then we end up with a negative delta G because the T delta S term becomes greater, and so the reaction becomes feasible at higher temperatures, which is why thermal decompositions require energy to be put in. The final example then, or I should say permutation, is if we've got a positive enthalpy, in other words an endothermic reaction, and we are decreasing the entropy, in other words we've got a negative entropy. In this state, delta G is always positive and the reaction is never feasible at any temperature. Okay, we're now going to have a look at this example reaction of zinc decomposing on heating and see if we can work out whether the reaction is feasible and at what temperature. So A says to calculate enthalpy change, entropy change and delta G for the reaction at 298 Kelvin. So first thing to do is the enthalpy change. Now we've got formation data here that we're given. So enthalpy of formation, if we're trying to work out the enthalpy of the reaction, we do the enthalpy change of the products minus the enthalpy change of the reactants. So products minus the enthalpy change of the reactants here. And so in this case we would have minus 348 plus minus 394 take away minus 812, and that gives a total of plus 70 kilojoules per mole. The next thing then to work out is the entropy change. So delta S is equal to the entropy of the products minus the entropy of the reactants. And so in this case we've got 44.0 plus 214 minus 83.0, giving us a value here of plus 175, importantly here, joules per Kelvin per mole. And this means that the Gibbs Free Energy delta G is going to be 70, remember to convert here, 1000 joules per mole, minus the temperature, and we're at 298 Kelvin, multiplied by 175, giving us a value in this instance of 17850 joules per mole, or if we convert it to kilojoules per mole and round it to three significant figures, we get 17.9 kilojoules per mole minus 1. Importantly for our discussions, we can see that delta G is positive, and therefore the reaction is not feasible at 298 Kelvin. So the final thing to do then is to determine at what temperature the reaction is feasible for the zinc carbonate thermal decomposition. And so here we say delta G is equal to 0, and therefore 0 is equal to delta H minus T delta S again. We can see that we have T delta S equal to delta H, and then the temperature at which it becomes feasible is delta H over delta S. And so taking from our previous values, we now have 70,000 over the entropy value there, which was 175. So ensure that you convert your kilojoules per mole to joules per mole, otherwise you're going to have some slightly funny answers. And we end up with a value here of 400 Kelvin. And the reaction will become feasible at temperatures greater than 400 Kelvin, since the entropy value is positive and the enthalpy value is also positive. The final thing to consider then is perhaps some sort of graphical math skills that we could be asked about in the exam, which could potentially be new this year. They certainly haven't asked these sorts of questions in the past, but it's just to consider if we plotted for a reaction the Gibbs Free Energy, delta G, as a function of temperature, and we considered here the straight line graph y is equal to m multiplied by x plus c, where y and x are coordinates, m is a gradient, and c is the y-intercept. Well, then if we're looking at delta G is equal to delta H minus T delta. Of course, the graph doesn't have to be the same as the one we've just seen. It's just as likely that the delta G is 0 at 800 Kelvin here, and that the reaction is feasible at all temperatures up to and including 800 Kelvin. And this is because in this instance we've got a negative enthalpy change and we've got a negative entropy change. Okay, thanks for watching. You should now be able to explain, describe and calculate changes in entropy, and explain and describe Gibbs free energy and how it relates to enthalpy and entropy changes to the feasibility of a reaction. Do remember to check out the cards here by clicking on the I button for links to other videos as well as relevant polls. Do share and like the videos, and I'll see you again soon. Bye for now. S. Then we have values for delta G of y here. T would be our x value, which means that delta S here would be m, our gradient, and delta H here would give us our value of our intercept, C. Therefore, from this reaction, we could calculate a gradient by doing the change in y by the change in x to give you a value for the entropy change, delta S, where we intercept here the y-axis. This would be our value of delta H. And importantly, as we look at our graph here, this point here where we go delta G is equal to 0, this is our point at which our reaction becomes feasible. Looking at this graph, since the line as we go to increased temperatures goes more negative, then this is feasible at all temperatures greater than 300 Kelvin.